Okay. All right. So, good morning, everybody. So, welcome to the first of the 3 Apops sessions. These sessions are really designed to try and give the technical and operational community a forum to present current, latest, greatest things happening in the internet industry. And also just generally share views and so forth. During the Apnic conference. The Apnic conference is not just all about policy and internet governance and so forth. It's a very important part of the technical community meeting calendar as well. And so the Apops session has been part of the Apnic conference for 8-9 years now. And, this has been a good opportunity for the network operators to participate. So we have 3 sessions, as I was saying. Apops background, network operations group for the Asia-Pacific Internet. The 3 of us who chair it, myself, Philip Smith, we have Tomo Yoshida, who sends his apologies. He's not able to be with us this week. And Maz from IIJ, who's going to be one of our speakers and is waving over at the side of the room there. Website, we have mailing list. Thankfully, the mailing list is relatively quiet. In some ways from noise, we generally cover a little bit of technical content, state of the routing in the internet in the Asia-Pacific region, as well as some of the major announcements affecting the Asia-Pacific internet. It could do with quite a lot more traffic, but such is life with a lot of the mailing lists. I guess these days various other media have replaced the good old mailing list. As I was saying, Apops is here at Apnic 38. It's part of the regular Apnic conference program, has been for many years. We did a general call for contributions, probably starting about 3 months ago. The program committee is actually the program committee that assembled Apricot in Malaysia in February this year, and the PC very kindly stayed on to help build the technical content for this conference. Before we jump into the agendas, we have lightning talks on Thursday. So these take place after the policy SIG finishes. I like to see them as light relief after the policy SIG. Maybe that's the wrong way of presenting them as well, but it's certainly after the deep policy discussions, it's a good way, I think, for us just to relax a little and hear some of the current topical, maybe slightly off-the-wall presentations. The call for lightning talks opened a couple of days ago. We've already got, I think, 5 or 6 submissions, not saying they'll all be accepted by the PC. We have room for 8, so if you're interested, please do submit your proposal. Don't need slides, but as long as you can explain in the abstract roughly what it's all about. Might be easier to go to the Apnic conference webpage rather than memorizing that URL, but please do submit. We have room, as I was saying, for 8 lightning talks. So that will take place Thursday after the policy SIG. And to the agenda. So we've got 3 sessions. I'll quickly run through each one. I'll come back to the slides for today's agenda. This afternoon, we have 3 presentations. So the BGP monitoring protocol testing by Janog, what is actual internet speed by Sung-Il Lee, and then we have Paul Vixie talking about passive DNS collection analysis. And to appeal to you tomorrow morning, we've got Tony Hain talking about a vast array of small-scale providers with gigabit access. Apnic, Agustin Formoso talking about Latin American and Caribbean internet connectivity, and Jeff Houston talking about what's special about 512. But back to this morning. So we have 3 presentations. First up, we have Jeff, who will be talking about DNSSEC validation. What if everyone did it? Of course, this conference is webcast. We also have the live scribing that's happening on the screen to my left, on to your right. So as ever, I would ask our speakers and questioners to please speak clearly, as I hope I'm doing. Also, if you're going to ask questions, please state your name and affiliation. It's as much for folks who don't know you here in the room as for folks on the webcast, so we know who's asking the questions. Thanks. So, Jeff?
Thanks, Philip. Good of you brave souls to make it out here this morning, when all your compatriots are still fast asleep. Yes, I'm Jeff Houston. I work with Apnic, and this morning we are going to talk about the DNS. The DNS is a miracle, an absolute miracle. You imagine in civil engineering, you design a bridge to cope with 1 metric tonne of load, but across that same bridge is not just 100 tonnes or 1 million tonnes, but tens of billions of tonnes across the same bridge. The scaling factor would be impossible in the physical world. Yet fascinatingly, the DNS, which was originally designed when the internet had, about 100,000 nodes, and managed the phenomenal rate of a few queries probably per second when it was really working hard, now encompasses 2.7 billion users and handles a load of queries that defies belief. Same system. Exactly the same set of protocol mechanics. It's amazing that it works. And what's even more amazing is none of you know it. None of you notice it. You type URLs and the web page appears. And it's blindingly quick. How did we do it? Don't ask me. Go and ask Paul later on if you find him, because he was partially responsible. However, there was one thing that kind of happened a little while ago, 2 years ago to be precise, that was sort of a bit of an eye-opener. IANA now runs a DNSSEC-signed DNS route. Do a great job, fantastic. And up until about 2 years ago, almost to the day, they were doing around 3,000 queries for the root key per month. Fine. Folk want a root key, get hold of it, keep it for a while, ask in a few more months, nothing's changed, this is good. In September 2012, the number of queries for the root key jumped up to over 30 million. Step function. Just bang, everyone wanted a root key. And there was a certain amount of head scratching until they started to look at who was asking and why. And what it turns out is that Apple had just released iOS 6, and as soon as the thing came up, it said, I want the root keys. That was what was causing this. But what was interesting at the time was that while they were asking for the root keys, they weren't actually doing direct DNS resolution. They were still using caching forwarders and so on. They hadn't actually put a full DNS resolver into these devices. But when will they? Because at some point, I reckon it's going to happen. Because right now, DNSSEC is great, but incredibly obscure. And quite frankly, spotting the difference almost beggars and defies belief. What's the difference between those two queries? Well, they're those two answers. Because when I dig for one domain, it comes back with a bunch of flags and a bunch of answers, whoopee-doo. And when I dig for a domain that's sort of similar-ish, it comes back with almost the same sets of flags and an answer, and it's really, really hard to tell that the crucial thing is that one has a flag, AD, and the other one doesn't. Kind of, so what? And what happens when you get a response that says, no, sorry, can't answer that, the server's failed? Well, generally that means try somewhere else, doesn't it? Except in the case of DNSSEC, which you're magically meant to understand that this is a dud validation and you shouldn't even be trying to resolve that answer. You know, this DNSSEC stuff is brilliant, but fatally flawed. Because the kind of signalling that we use really isn't very robust. If I was a man in the middle between you and your favourite resolver, I could insert or delete the AD bit at my whim. Where's your protection then? And similarly, how do I know that serve fail really means DNSSEC validation sometimes, but means the server failed in other times? This is kind of weird. So a number of folk have been sort of trying to say, well, we need to fix this. We need to secure the channel between you, the client, and your resolver. We need to do key exchanges. We need to run secure UDP. Yeah, right. All of a sudden, the DNS becomes like molasses. It's no longer fast. That's kind of crap, Rep. So this leads to this thought process that goes, you know, there is another way of doing this, and it's actually not all that hard. What if inside the actually mind-bogglingly fast processor and scubs of memory and huge amount of operating system in here, what if I put the DNS resolver right here in every device? Just run DNS everywhere. Use the same caching infrastructure, use the same resolvers, but don't take their word for it. Do it myself. Interesting thought experiment, because I think the world would be a better place DNSSEC-wise, because you don't have to trust anyone else, you're doing your own validation. But this little salutary lesson from running the root keys becomes a real issue. IANA is now doing a load of up to 30 million queries per month, probably higher these days. What about you if you were an authoritative name server? What would happen if everybody was doing DNSSEC? So, geez, I went forward about 5 million slides, sorry. This thing's got bounce. So what can we say about a DNSSEC environment where everyone does their own DNSSEC validation? That's the kind of question we want to look at. So, oh, by the way, you people are on the left-hand side, losers. The slides are over this side. Feel free to wander over. And the further you are on the left over there, or my left, the more you're losing, sorry. Either that or the slides are online. Back to the slides with the tiny writing. DNSSEC today covers around 12% of the internet user base. And you kind of go, that's a really, really, really interesting number. V6 today covers around 2% of the internet's user base. So in one respect, without an awful lot of fanfare, DNSSEC has had an astonishing success. That's the kind of up and to the right graph that V6 would kill for. Because it's a huge amount, you know. 1 in 6 folk, one way or another, are doing some kind of DNSSEC validation today. Brilliant. So what if everyone did it? What I really want to look at this today is, what if we got the other 88% of the internet and we all did DNSSEC? And what if every device said, look, don't trust the rest of the world, my validation, my keys, my validation? What would be the difference in load, and how much longer would it take to do validation? Is this a dreamable dream, or would this all collapse? Too much load, too much everything would go slow. So it's kind of a way of using the data we already collect and see if we can bend this around to answer that kind of question. Could we scale the DNS up to everybody performing their own validation right now? What's the difference in load? So currently we serve a Google ad. Google's brilliant, their ad system is fantastic. It reaches most of the planet most of the time because most of you watch YouTube instead of working. Keep doing that, it's a wonderful thing. We get ads presented everywhere. The ad does 3 invisible fetches of a pixel. Now, the pixel is irrelevant, don't care. But the DNS of that URL are 3 different forms. One pixel has a DNS domain name that's completely unsigned. It's just vanilla. So there's no signatures attached. It's just a normal, or abnormal these days, a normal DNS name that's not signed. The second one I've deliberately signed, and signed with a conventional RSA key. So it's signed from the root. If you go and do validate, big tick, everything works. And the third one, just to pose a little test for these resolvers, is badly signed. I've deliberately gone and stuffed it up. It's as if someone is attacking you. There is no good signature on this. It does not validate. If you're a validating resolver, you should not fetch that URL, because you cannot resolve it because the validation will fail. So what am I looking for? I'm looking for folk who perform validation. So what does it mean in that context? I should see you plowing through the DNS for all 3, but over in the web server, because you're asking for a pixel coming from my server, you should only see 2 of the 3 fetches. You should see the unsigned and the good. I should not see you fetching the badly signed thing. And that's the kind of signature that says you're doing DNSSEC. So, what we saw, because the DNS is always approximate. It's one of the least deterministic systems on the internet, which is truly bizarre and very, very weird. Resolvers are a law unto themselves, as the people from ISC will tell you. What we see are actually three kinds of users. There are folk who are really simple DNSSEC validating users. And there are folk who don't do it at all. They only ask for A records, they just do the standard, I'm not doing DNSSEC, what's this crap, just leave me out of here. And then there are folk in the middle. There are folk who seem to have a bet each way, who sort of ask for a few DNSSEC resource records and then go, stuff it, I'm going to fetch the badly signed thing anyway. How does that happen? I don't know about you, but from time to time when I get into a really crappy hotel network, I add 8.8.8.8 to my resolver set. Yep. And typically I add it first, because Google's pretty quick most of the time. But sometimes I leave the hotel resolvers there as second and third priority. This is where life starts getting confusing. Because when I ask Google for that badly signed domain, do you know what it says? Serve fail. It doesn't say, that's a badly signed domain, Jeff, don't bother. It says, Google, failed. Go try another resolver is the subtext. So then I go and try some other local hotel resolver and it says, here you are, here's the A record, go there. And a lot of folks sort of fall into that bucket. In fact, 10% of the internet falls into that second bucket, where they have this sort of validating resolver, but then they have another one that doesn't. And when the first one fails because the signature's bad, they just go and use another. So I kind of see three bunches of people, the good, the bad, and the ugly. And what you see there is the blue is kind of the bad. They're not doing any DNSSEC validation, and that number's slowly declining over time. There's the red that's validating, those are good folk. And there's that green line that says, I'm using a bunch of resolvers, only some of which validate. And that line too is growing slowly over time. So how do I know how to validate? I get back this signed record from the DNS that says, this is the response, this is the signature. So I look at the signature and go, but what key was being used? Oh, you're going to have to fetch that. So I go and fetch the zone key, one fetch. And I look at the signature and go, well, that looks pretty good, but is that zone key real? Oh, I need to go up to the parent and ask the parent for a hash of that key, DS record. So I have to fetch that. Is that a real one? Well, I have to fetch its zone key. I have to go all the way back up. So what goes on when you try and do resolution is you start asking for more and more resource records. So at my authoritative server, what I see, if you're dual stack, you'll ask me for an A record and a quad A record. But if you are a validating resolver, I will see minimally a query for a DNS key record. And if I'm also serving my parent, because I haven't got too many resolvers, I'll see a DS query as well. So I'll see more queries. And that's typically what you see when you're a server. You see the original DNS queries, and then you see a whole bunch of validation queries spinning up towards the root. Standard stuff. But it takes time. So if I sign my name, my DNS name, potteroo.net, will your resolution of my name take longer? Am I adding to the wait time on that essential click? So here's the graph of the mean distribution. The blue are the folk who don't validate. And basically, there is no time difference. They're the normal distribution. That takes no additional time. But look at those green and red lines. For the entire planet, it takes between 250 and 300 milliseconds longer to resolve my name. Longer than if it was unsigned. Why? The server is in America. The close peak that you can't actually see is US, the second peak is Europe, the third peak is Asia. This is kind of the global distribution of RTTs reflected in the DNS. So what it looks like in some ways is there's a time cost going on for signing your name. And the cost of these additional queries required to validate the signature. And the approximation, it's about half a second longer. Now, as anyone would tell you in the $1 million millisecond game, that's a fortune. That signing the name adds a burden of time that is just too long. That is just unacceptable. You can do a bit more mucking around, and here's a time distribution of cumulative distribution of this, and I'll go a bit further. No, it's not there. This graph is also interesting about the fact that the DNS doesn't work well for everybody. Look at that blue line again. 80% of folk do a resolution of an unsigned domain in one query. Yep. But up at the top, the others don't. There's about 10 to 15% of the internet that has trouble resolving a simple name. So while most of the internet works with most of the DNS mostly brilliantly, there's a subclass of folk, the internet must be a trial and tribulation because the DNS just flounders around and takes forever. When you add DNSSEC, about 75% of the folk get the stuff done in half a second and the rest take longer again. So the time cost is certainly up there. Why does it take so long? Don't forget the DNS is UDP. So when you send out a UDP query, you sit there and wait for an answer. How long do you wait? Well, if you're Microsoft and you're running Windows, which a lot of the world does, you wait for exactly 1 second and send the question again. And then you wait for another second and send the question again. You see those peaks at 1, 2, 3, 4, 5, 6, 7, 8 seconds? That's Microsoft's timers. In fact, it's not just Microsoft. A lot of resolvers do this. Because the DNS UDP never says no, it just doesn't answer you that way. When you don't get answers, you keep on asking at regular intervals. And that's what we see going on and why DNS resolution takes so long when it doesn't work properly. So I want to compare signed versus unsigned for the client. And what I see here is a direct comparison. The red line is, this is the time penalty when it's unsigned. And the answer is, most folks, 75%, resolve a name in one query, 25% of the internet takes more than one query. Wow. When it's signed, that sort of 75% moves out to half a second, what we've already seen. So that's the kind of time penalty you can expect if you're doing a signed name. Or is it? The first thing I'd note is that most resolution software is brain dead, including the stuff from ISC, I am sorry. Because when you do that validation path, you actually know what queries you're going to make, and you could make them all at once. You could do it in parallel, but most resolvers don't. They ask for the DNS key and wait for an answer. Then they ask for the DS and wait for an answer. Then they ask for its DNS key and wait for an answer. And the entire thing is a serial walk back. That takes quite some time if you have no effective caching or your caches are fresh. Once the caches take over, it's quick. But you kind of sit there and go, you know what you're going to ask. Parallelism is what makes things go fast. Why don't you just do the lot at once? I mean, you could be able to cope with this, can't you? It's just standard DNS. And if you actually did this right and did a parallel stack of about 10 or 15 deep, validation takes one fetch cycle instead of 8 or 9, depending on how deep you are in the DNS tree, which would improve that resolution time amazingly. And the other thing about this, of course, is that clients are quick. Clients move. So if this takes half a second, does anyone drop out? Will signing a DNSSEC on your domain name cause folk to walk away from you? Obviously, folk like Google are very, very worried about that kind of question. Probably as is Microsoft and others. Time is everything. If clients can't resolve you, that's a disaster. So we looked. And this is a rather noisy graph, but what I'm trying to do is compare the dropout rate for a signed domain against the number of control points in this experiment. And the basic bottom line is, I can't see it. The good news is, as long as you don't use massive signatures, as long as you're not doing a couple of kilobytes of answer, if you keep your answer below one packet, 1,500 bytes, there's no visible dropout. Signing a name does not cause clients to lose heart with you. They will resolve irrespective, which is a great piece of news. Is it as bad as I'm making out? Well, actually no, it's a lot better. Because the one thing I do in this experiment is hand you fresh names. Every name is unique, there is no caching. So the standard DNS speedup, the local cache, is not being invoked. Were caches being involved here, you would not notice DNSSEC at all, because the validation would take, as far as I can see, at most 1 or 2 additional single cycles, if at all, depending on the cache state. So that additional overhead can be brought way, way down. So for clients, signing the name appears to be benign. Clients aren't going to walk away, clients are still going to resolve, and the resolution with caching is going to be fast. But let's flip to the other side. You're now an authoritative name server. You have a certain amount of capacity on your machine, you have a certain amount of bandwidth, all the names you're serving are unsigned. What happens if someone says, I'm going to sign my name now? What's the difference in queries and traffic at the authoritative name server when you move from unsigned to signed? Well, the first thing is, it looks a little bit like a DDoS attack, because the volumes you're serving in queries are now a lot larger. Unsigned, 120, 160 bytes, something like that. The DNS queries are small, the answers are small, 200 bytes of answer at most, nothing special. But when things are signed, you've got to serve the keys, and if you're using RSA keys, it's going to cost. And this is an example from mine. The A response with the signature inflates by 1,000 bytes, and there are these 2 additional queries for the zone key, which is another 750 bytes, and if you're serving the parent as well, the DS key, which is the hash of the key, that's another 350 bytes. All up, things inflate like crazy. So what do you see? 13 times the traffic volume. Looks like a DOS attack. All of a sudden, there's a whole lot more traffic leaving your server. And so look at that graph there. This is my server. The red is the control line, an unsigned line, and the green is the traffic I serve from a signed domain. And it's around 4 to 5 times higher, even when only 20% of clients are doing some form of DNSSEC validation. So you do see more traffic. If 20% of the clients generate 7.5 times the traffic load, you're going to see 20% of the clients generate 13 times the traffic. That's a little bit too much. What's going on? The DNS is, again, weirder and weirder and weirder. Most of the time, most folk ask for a signature even when they don't use it. So most of the time, when you sign a name, all of a sudden you'll find that most of the queries that come at you want that signature, even if they don't use it. 84% of the queries have that, give me the signature anyway. So as soon as you sign a domain name, you're going to get more traffic, irrespective. And when everyone performs validation, that'll go up to 100%. So roughly what we see is around 7 times the traffic. That's about right. So what happens there if everyone does it? If everybody on the planet did validation, you will serve around 15 times the traffic load. Which, if you're handling a reasonably good authoritative name server, you probably have that margin for DDoS anyway, because at some point you're going to get traffic spikes because people are just going to use you to bounce traffic against victims. So that's okay. What about the query load? Well, the query load is, again, you're going to see about 2 to 3 times as many queries. Yep, and that's approximately what I see, 2 to 3 times as many queries coming in, because I've got to pull down those additional queries. But I actually see more than the theory. Why is that? We increasingly see the DNS used in server farms. Google is a classic example. 8.8.8.8 is not a honking great machine, it is a bunch of machines. And sometimes, just to be sure, the query is fed out to multiple slaves to resolve, not just one. So one initial query over in the sort of client end asking 8.8.8.8 turns into 2 or 3 or 4 queries coming at you, the authoritative name server, because the query is being duplicated in the farm. And we're seeing that certainly rise over time, that there are more and more farm cache prep queries as distinct from queries for clients. This sort of redundancy that's being built into the caching network of the server farms causes additional traffic over at the authoritative name server. So, that's a classic example coming in from Google of this kind of really rapid fire, and they're spaced at 2 and 3 milliseconds apart, rapid fire queries from multiple entries in the same server farm. That's rising. So, if the domain is well signed, you can expect about 4 times the query load, about 15 times the traffic load, if everybody on the planet did DNSSEC. Not a big number, not scary, not worried. Sort of. Problem is, as usual, if you let your signature go bad. Because when the signature is invalid, serve fail does not say, I'm bad, go away. It says, I failed in the quest, O master, try somebody else. And you do. And you query and query and query. How much worse does it get? Well, this is for a badly signed name. And you notice that little peak over there to the far right? Sorry, you people over there, you can't see this. There's a peak over there at around 2 seconds. Because this stuff is astonishingly sticky. That they sit there and just pound away for many seconds before they eventually give up. Because when the thing is badly signed, serve fail is not the right answer. 25% of clients can keep on going 6 seconds later. You, the user, have gone away, but the resolver's been going, I've been given a task, got to try and get a valid signature out of this mess. And so what you see is that the relative traffic profile, once your signature goes bad, keeps on getting higher and higher. It goes up to a factor of 10 times and gets worse than this. What if everyone validates? What if everybody on the planet was validating and your signature's bad? Well, this kind of predicts you'll see about 30 times the traffic load, which is a lot. But the problem is that it's even worse than that, because caches don't cache crap. There's no point caching rubbish, so they don't. And so now there's no caching leverage. When your domain signature fails, no one holds you in their cache anymore if they're validating, because you're bad. And so every single query comes back to you on the authoritative name server because nobody is caching you. And so that cryptic serve fail causes bad signatures to explode, because now all of the resolvers you're using pummel all of the name servers all of the time because it's a bad signature. They can't cache the answer. So you can expect around 4 times the query load and about 15 times the traffic load if your signature is good, if everybody did it. But if your signature goes bad, not only will no one be able to resolve your name, which is bad, but at the same time your authoritative name server is going to get a minimum of 8 times the traffic load, possibly higher, and a minimum of around 26 times the traffic load, 8 times the query load and around 26 times the traffic load. So you're going to get a vastly larger amount of traffic. Have we seen this? The RIPE NCC was one of the early adopters of DNSSEC and started signing the reverse namespace of the IPv4 addresses that they were authoritative. Every 6 months they rolled their key, which is perhaps a little bit too enthusiastic, but it was a regular good practice. Roll the signing key, just keep moving. So you prep a key, you sign it, you move on to the next key. And every single 6 months, the traffic profile on their servers went up. Why? Because over there in Linux land, I think it was Fedora, but one of these distributions was doing a package distribution of DNSSEC that included the original key that RIPE was using. So every single time RIPE rolled the key, the folk using that particular operating system and that particular distribution had a bad key. They thought the signature was invalid. So what do? Start asking and asking and asking and asking. And every 6 months, the number just increased. So this is not an academic study. The issue is, once you start signing, the one thing you really, really need to look out for is don't ever let your keys fail, because that would be really, really bad. Thank you.
Thank you very much, Jeff. Are there any questions? No questions at all?
Thank you.
Oh, well, thank you. So next up, we have Maz, who is going to talk about finding the path. So while Maz finds the path to the microphone, you can follow Apnic38. Of course, the Twitter hashtag is on the display behind me, #Apnic38. And don't forget, it's being webcast as well. Not that you would need to watch the webcast if you're sitting in the room here, but if you're watching the webcast, again, feel free to funnel questions the usual way. All right, over to you, Maz.
Okay. Good morning, everyone. This is Yoshinobu Matsuzaki from IIA. Today, I would like to talk about finding the path. I'd like to share two things today. Number one, understand your network and needs for cooperation. If you're a network operator, you should know about your network, because sometimes you need to fix your network once you have problems there. Not by guessing, not by assuming, not by random practice. Sometimes operators do that. But you should know about your network, not only your configuration, not only your design, but also behavior, right? So let's think about a case. So today, what do you need to consider once your customer faces the reachability issue, right? You need to find the path that the customer uses. So we need to find the path. We can presume the outgoing path by using the routing information, BGP or traceroute. But still, the user might use the different path, because it's depending on the source network and the destination. If we are operating the AS BGP network, usually you have a multiple exit point where you are interconnecting with other network AS. And BGP usually prefer the closest exit if other preference, like a local preference or a MED, looks the same. From POP 1, if you want to get the destination Z, then the packet going through the ISP A, and POP 3 as well. But from the POP 2, the path through the ISP B looks closer to get the ISP Z, right? So even the one network uses a different or several paths to get the destination Z in this case, right? So if the customer located in the POP 3, and you are operating from the POP 2, and check the path by traceroute, you are seeing the different path from there. So you should know about your network. And also, in this case, once you change the IGP cost inside your network, that can also change the exit point, right? So by changing IGP cost inside your network, that change the outgoing path from the POP 3 to get the destination Z. So it's not consistent. It's based on your IGP configuration. It's your network behavior. So you should know about this. And today, we are using multipath more and more to get more bandwidth. And still, it's the 10 by 10 is cheaper than 100 gig. So people using multi-pass to get enough capacity with a lower cost. Like you want just a 4 gig rather than installing the 100 or 10 gig physical interface there. There are several techniques to aggregate the links. Based on layer 2, you can use the link aggregation. And layer 3, we can use a multipath based on the dynamic routing protocols like IGP, equal cost multipath, or BGP multipath. There are several operational differences between layer 2 link aggregation and layer 3 multipath, especially the case when you have a failure there. But it's up to you. It's up to your design network. And there are two major load sharing modes for multipath: power packet load sharing and power flow load sharing. Power packet load sharing is good at load sharing for the equal load sharing, but it has a risk for misordering that may break communications, like IPsec or some secure communication. So I'd highly recommend the power flow load sharing if possible. It's good for packet ordering and consistent delays. Right. And if you use the power flow load sharing, it's still based on the equipment and the software and the firmware of the device. Usually, it uses a flow defined by the source IP and destination IP and protocol and the ports sometimes. And most devices use a sort to get efficient balancing. Usually, a device generates the random value when it's boot up. If you have a multi-stage multipath, like several routers layers, you can get the efficient balance by this sort. This is an example multipath inside IIJ. I did a trace route from my host to the ftp.iij.ad.jp. And this is our network. I know how many paths we have inside our network. So first hop, just one path, and second hop, we have 2 paths, and third hop, 1 path, but still we have one backup there, and next 6 paths, 2 paths, 4 paths. So we have many multipaths inside our network. The combination now, 96. Right? So if you perform the single trace route, it can only one of the 96. Right? So if there's a failure, some links, just like a packet loss or unusual delays, you need to find the exact location. So you need to care about your network behavior. And next, cooperation. We are ISP. Of course, we are maintains our own network, but it's just part of the internet. Most part of the internet are operated by others, right? So it's out of our control. So once we have a reachability issue or a network, internet-wide problem, we need to cooperate by sharing information, by exchanging knowledge. So example, probably you need to find the reverse path as well to fix the reachability issue. But you have almost no clue. BGP cannot tell much about the reverse path on your side. It's also difficult to guess because other ISP have their own business relationship, like preferring their customer or preferring some special path, depending on their policy. But still, we need to do that to fix the issue. And I'd like to share about the return path from the intermediate node may vary. Okay, let's assume we ask the trace route from destination Z to our client, right? So they trace route, okay, in this case, they prefer ISP-B to get the POP3's client. Okay, trace route, one hop coming, ISP-B, return packet, and coming to the POP2, the return packet goes through the ISP-B. But once the packet reaches the POP3, the return packet goes through ISP-A. Right? So this case, until to get the POP2, the return packet goes through the ISP-B. But once it gets the destination, the client in the POP3, then the packet going back through ISP-A, totally different path. So also we should know about this. There are several ways to check the reverse the return path. As ISP and the BGP operator, we are sharing routing information on the looking glass. You can check others' BGP tables there. There are major looking glass like RootViews project. They have a Telnet and CUI interface to check the BGP table. And also RIPE NCC is operating the routing information service RACE project. They have a nice web UI. Of course, there are many others maintained by the volunteers. This is an example of RootViews. You can Telnet to access the route view or server. And here, they said, please use our views as username. So I entered our views as username here, then you can log into the system. Then you can check the routing information. Sorry, this is not Sanog website. It's I checked route to the Apnic website. Yep, something like that. So you can take the BGP-S path from the looking glass. And many AS operators provide a full routing table to the looking glass. You can check the others' BGP table there, like this. This is an example of RIPE RACE looking glass. Again, you can enter your destination here, then they give some idea about routing information here. There's another effort, NLNOG ring. It's a project to share access. It's exchanging share access. Once you install a Linux box and give them a control, then you can get the SSH share account that can log into the ring node. It's quite useful for debugging of network reachability issues. And today, I think about 260 is numbered participate in this project, including IIJ. Yes, because it's based on the Netherlands node. Most nodes are located in Europe, but still we have several in Asia Pacific as well. This is an example. I did a ring ping. It's a ping to the destination from the whole ring node at once. So you can get the result from the 260 node like this. And then you can get the result, the summary as a result. So from 260 servers, the RTT average about 300 millisec, because it's mostly based on the Europe. And one unreachable here, yes, they have some network issue, OCCAID01, so it should be okay. So you can check your connectivity from the whole ring node at once. That's a good tool. And also you can trace route from the particular node as well. It's also useful to check the routing path against you. So the internet is composed of simple things. We are just part of the internet. But still, we have a very limited views of the internet. Yes, we can do trace route, pings, routing tables, but many parts of the network are hidden. So that's why we need to cooperate. And also, at least, you should know about your network. That's your part. And based on that, we can cooperate to have a better internet. That's all.
Thank you very much, Maz. Any questions before you run away? This is a very quiet morning.
Yeah, still, it's morning.
It's morning. Oh, okay. So we're going to have lots of questions in the afternoon then. Oh, well, you get off lightly. Thank you very much for that. Next up, we have Eric Vink, who will be talking about leveraging IPv6 extension header for traffic engineering.
Yeah. Thank you, and good morning again. So, there's a very cryptic title, isn't it? So I hope at the end of this talk you understand better what I want by leveraging those extension headers there. So we know for sure, and it's pretty nice to see here at Apnic meeting that IPv6 is cited on each and every talk, including, let's say, the normal keynote, not only the technical keynote. So that's really, really good. We know IPv6 is there. We know it's doubling every 9 months average. So point taken. And pretty much like Maz has said, traffic engineering within an AS is not always easy. The way it's done most of the time is using, for instance, RSVP to install specific thing. Meaning, in this case, that if you want to get a path going that way, you need to install a lot of states into your router. It takes memory, it takes CPU. In short, it does not scale. But there's the way to do it, and we are hitting there some limitation. So what about to do something which is more scalable? Applicable to IPv6 and applicable to MPLS, by the way. The trick is that when a packet arrives at your network, assuming here it has the IPv6 version, from A to B, at the ingress point of your AS, a kind of let's say again, to use a bingo keyword, SDN controller or whatever, basically talk and say, hey, you are this traffic from A to B with this protocol and this 5 tuple or whatever, then you should follow this path. But oh, simply by using, and looks like an offense for some of us, the source routing. Yes, we are back 25 years ago. Why not? Source routing has been designed for good reason, right? It has been canceled for other good reason, but we can reinstall it for good reason. So basically we say at the first hop, we inject the extension header source routing, tell, hey, please go this way, and this way. The beauty is that now the internal routers inside do not have any states. The states are in the packets into the routing header, which is much more scalable. That's changing completely the game. And I see some people in the room scratching their head, but that's fine. Again, the big benefit, no state in the core of your network. That's what we mean. So, in a nutshell, what's this? Already explained. Use source routing, and of course, we need to fix the security issue of it, which is the reason why, as a security person, I'm talking here. And it's basically reusing a very old architecture from 1997, right? RFC 2460, which is basically the IPv6 spec. So you may want to go to a website where all the specs are centralized. Of course, they're also the ETF. You should simply know that it's coming from the IPv6 version, but not so many networks at the core run native IPv6. A lot of provider network is based on MPLS. So we needed to find a way to do the same kind of techniques for MPLS network. So there are two data planes for what we call segment routing, because we have simply assumed the list of segments, pretty much like the naming, into the routing header. The way we do it in IPv6, that's by using the routing extension header. In the case of MPLS, we are simply stacking a lot of stacks of labels. So as I said, multiple drafts at the IETF. I put there the two main ones for v6. There's a third one that I wrote about the security of it. If you look about the names, it's not only vendors, right? There are two providers inside because they really, really want to do quality of service, traffic engineering in pretty large network. Okay? Comcast and Rogers are pretty large network. So, oh, and by the way, coming back one slide, as you know at the IETF, most of the working group names must be fun. So this one is Spring, which means source packet routing in networking. So at least we can get a smile by looking at it. So the source route, in the case of IPv6, is pretty well known. So for instance, on the top diagram we have here, we want to go and follow the blue lines, right? Going from A to B to C, F, G, and H. For any kind of reason. Could be cost, could be quality of service, could be whatever. So how can we express this? And still leveraging a few things. If you remember source routing from your old school days, there are two kinds of source routing. Strict, where each and every hop must be specified, and loose, where you specify only a few hops on the path. So in this case, if we use loose mode source routing with only specification of C, F, and H, then we can use the equal cost multipath between A and C, some packets going over B, some packet going over E, and then after when reaching F, there is only one path. So we can simplify somehow as well the operation there. So remember, at the ingress, when the packet arrives, it does not have extension header for routing, we simply insert it. And of course, we need to do the usual magic or the usual processing to follow routing extensions. So if you look about change field, there are some fields that are in red now. Because if you look about the destination address on the left packet, it was Y, because Y is completely on the right-hand side. That's the final destination across the ES. Now we need to set the next hop as being the first segment. So we say now destination address, DA, equals C. Okay? And we have a pointers, if you remember, into the routing extension header, there's a list of intermediate hops, and we say next one will be this one. Okay? So in the segment list, SL, I put in red the next one, that would be F. So now, but talking about the segment routing header. So at the very beginning, we wanted to use the routing extension header, the type 0, but it's too ugly regarding the security, so we need to change it. But still looking at it. So it was a version we proposed at the IETF in Toronto. Just beware, we'll get a new version with some minor change, mainly in the flags. But it's a normal extension header, right? We start with the next header, the length, routing type, and it will be not an existing one, and the next segment, basically the pointer there. Some flags, and you will see as well HMAC, like a hash message authentication code. And this is very key if you want to get security there. So, complete picture now. Packet arrive at A, and we have seen we are changing it pretty much like I've described 2 slides ago. Next destination is C, and the next segment list is F. Arrive at C. B and E simply forward packets as usual. Okay, they do not need to be segment routing enabled or whatever. They see an IPv6 packet going from source X, destination C. They forward it pretty much like any existing IPv6 packets. Arrive at C. C is segment routing enabled. So this one says, hey, destination is myself. Oh, simply, pretty much like RFC 2460 says, let's process it. So meaning, new destination address is becoming F. Again, pretty much normal source routing in IPv6. And I increment as well the next header. Now it's H in the list. And then we move it to H. And this one is specific configuration simply because he removed the packet. He's removed the extension header. It forced the path in your network. And routers in the middle can either be completely agnostic, they have no state anyway, and the one which are segment routing enabled, the one in blue, have no state, they simply need to process those packets. And the processing is pretty similar, if you think about it, as a source routing. Interesting case. In a specific case of data centers, people running data centers, whether a service provider or an enterprise, sometimes want to have packets follow a specific path because they want, oh, these packets you need first to go to a firewall, then to an IPS, then to a load balancer, and the other one, you directly go to the server load balancing. So different paths for different packets into the same network. That's called service chaining. And in this case, you want to say, hey, for this packet arriving in A, I want to go first to S1, let's say firewall. Arrive to S1. S1 is also segment routing enabled. So after processing the packet, it simply send it again, still with the extension header, with destination address being S2, because it was in the segment list, and the final destination is Y. Arrive there, then it's forwarded to node Y, and just before leaving the segment routing enabled network, we remove the routing header. Service chaining is usually for application people quite crucial. And that's one way of doing it without any MPLS. Right? Data centers usually don't have MPLS. But we may want to push this traffic engineering to what I call the extreme. What if you have a mobile node, could be a mobile phone, and with 4G, in some states, in some country, specifically in Europe, where roaming for data should disappear, right? Same price in your country is while you are roaming. So the only way to do it is by local breakout. Meaning I'm from a Belgian provider, I'm in France. When I go my data over 4G, I exit in France with a French IP address, okay, which is not the case right now. So if we want to conserve some traffic engineering in those cases from a mobile node, or maybe from over the top service, like video, what we can do is that the PC now, so outside of your AS, the PC or the smartphone, requests to the same controller, again, SDN or not, you don't care, to get the value of this source routing header it needs to exit. So now, from the PC or the smartphone, packets are sent with this extension header, the routing header, and it follows the same path. Of course, we know routing extension header are a source of attack. More to come on this. So when you enter the AS providing the service, the video provider or whatever, we need to check the validity of it. That's the role of the HMAC. Check the HMAC. The HMAC has been computed by the controller, and of course in relationship with all these routers. And then pretty much as usual, packets is forwarding hop by hop using this extension header. The HMAC is no more checked because simply we are within an AS, and within an AS, every peer router trusts its own peer. Okay, and then usual procedures. But maybe some people were afraid of using source routing. Maybe because it's outdated, but maybe as well because it has been deprecated by the ATF. But actually, only one part of it has been deprecated. So if you look about the routing header itself, you have something like this, routing header type, which appears in the third bytes. And currently, IANA has defined 4 of them, and number one is no more in use. We have type 0, which is the bad one, and we shall see why. We have type 2, which is used for mobile IPv6, which is perfectly okay for security. And we have type 3 for Ripple, the 6LoWPAN and so on network, which is also okay regarding security. So my guess is that for segment routing, we will get number 4 from the IANA, but not a problem here. So type 0 is the one we do not like. That's the one as a security person I say, please use your ingress ACL, drop routing at a type 0, because it's bad. And the reason is that with type 0, we can have a segment list which is long. Okay? Can be very, very long. So we can have a segment list such as this one, from A to B to A to B. You have the 2 routers. Let's say one is here in Brisbane, and the other one is in, let's say, New York City. And the bad guy, and look about the color of the hat. There's a black hat. It's not a white hat, so it's a bad guy, right? Send its packet with source routing. I arrive at A. Oh, next stop is B in my segment list. Oh, next stop is A. Next stop is B, and so on. Loop. Okay? Of course, up limit is there, and at some point of time, it will reach 0, and packets will be dropped and be removed from your network. But you have an amplification from 20-something, which is bad. So this one has been deprecated by the ATF. Routing at the type 2 is for mobile IPv6. There's a 2 at the right place. But for mobile IPv6, there can be only one segment in the list. So the amplification factor is maximum 1. Okay? So that's perfectly fine. And that's the reason why this routing at the type should be allowed in your network if you allow basically mobile IPv6. Type 3 has been defined by the ATF for Ripple, for the routing protocol for the low-Z and low-power network. That's basically the graph on the right describes a Ripple network. Think about smart meters communicating to the smart meter just for the house next door. Okay, so they can build somehow like a mesh, or actually in this case a tree of smart meters or whatever. And the only one they can communicate to the next one because their radio is not powerful enough to reach the complete zone. That makes sense. The way, and they are very small device, so if they're using stateless Ripple, basically the nodes have only one route, the default route towards the big blue router, which is the controller. Okay, so the packets coming from everywhere, from the bottom to the internet, will travel using the default route. Now, packet arriving from the internet destination, one of the smart meter, the blue router knows all the routes. There is a routing protocol there. Okay, that's RIPL. So now, when packets arrive from the internet, destination 1 smart meter at the bottom, it will also insert a routing header there to follow A. You need to go from A to C to B and so on. So pretty much like segment routing. And this one is safe simply because the blue router will forbid incoming routing header type 3 coming from the outside. Right? The routing header here is only used within the smart meter environment. So, and those smart meters or whatever are usually trusted because that's within one AS again. And you need anyway to have some layer 3 security on them for transmitting data. So that's the reason why this one has no security problem. So how can we do with segment routing? Simply by defining another type, so to differentiate from type 0, and we have basically two cases. Either we do a HMAC, meaning that the source of the packet, the one who inserted the routing header type 4, or whatever, has got the same pre-shared key as I have, me, my router. So meaning it's very easy to know the authentication and the authorization as well, that some node was able to use this specific extension header. Okay? It's not a signature, because there is no repudiation possible there, but it's a proof that you are members of those segment routing enabled nodes. And of course now, if you don't do it from the outside, you only insert it when you reach your AS, you don't need to do it. You simply reject packet having this router type 4 coming outside of your links, and you only admit it when it's coming from an interface belonging to a routers of yours. With this, there is no amplification possible, there is no reflection possible. So you don't have any security issue. Another question mark now that we've got. Hey, there are so many people that knows that routing type 0 is bad. As I said, I spend my life telling, please drop them in the ingress of your network. So what about segment routing? So let's say type 4. Normally this RFC 5095 that says, hey, source routing is bad, says drop only type 0. So don't drop the other one. So what's the issue? So we've done some testing, and if you go to this web page, when you are back home or here, you can try. It's basically, if you have a v6 address, it will send a ping to you using normal ping to your IPv6 address, as well a ping with a source routing extension header inside. So it allows to test whether there is a clean path. And I made multiple tests and some conferences where v6 was offered, like IETF conferences or others, and the tests were always successful. I must say that if you test it on this network here, it will fail. So most probably the Apnic network here drops all routing type 0 and 1, 2, and 3, or whatever. So the test is failing. But if you try with other destination like IETF or other website, it works fine. My point there, it looks like at least within one AS, you can use source routing if you configure it correctly, and using a very specific extension header that cannot do the amplification attack there. There is also a Bits and Bytes event at the IETF in Toronto in July, where multiple implementation of segment routing have been running. One in Linux, including the HMAC, coming from the University of Louvain, from my country. One Comcast implementation, and two implementations from Cisco. All of them were working together. And I think it's very important that we all agree on the format of this SRH, segment routing header, or also known as routing header type 4. And in the case of Cisco, it was also using existing hardware, and we were doing it in hardware, simply because routing extension header was already there before. So the ASIC, the silicon was there. It was quite easy to just change it somehow. Okay, wrapping up. And just to be in time so Philip will be happy and will get his tea on time or coffee. So segment routing leverage the source routing model that exists in IPv6 as well in IPv4 for many, many years. Yes, it's coming back from the ashes somehow, but we can do it in a secure way. And the best way is that you have stateless routers inside, and you can do traffic engineering, which is pretty good. Another point to note, not every node needs to be segment routing enabled. A segment routing packet, if you are not the destination, you only need to forward it by using the existing data plane that you have. So you can have very old IPv6 routers. They will work. They will simply see a packet from one segment routing node to another segment routing node for sure, but they simply forward it as any other IPv6 packet. So it's kind of a very smooth introduction in your network. You do not need to do it in each and every network. So standardization is in progress, and it's coming from multiple vendors, so there is kind of a good consensus there. It was not assumed at the beginning, because when we come back and the IETF say, hey, we need to do source routing, I can tell you people were not happy at all. They were, hey, what have they done, those guys? But the ID is getting more momentum there. So we can really expect something there. Code is running. There are beta tests if you want to do it. We are also planning to run a research network using over the internet a research network which is segment routing enabled. And we've got codes. I mean, speaking here at Cisco, not as IETF. So we can basically get things working and rolling. There's, again, pointers, and there's a mailing list as well as on the IETF. So I'm pretty sure, I'm not sure whether we have time, but I'm pretty sure it's a kind of a shocking topic for most of you. But again, it brings you stateless for the router traffic engineering, which is, I think, is a huge value. Thank you for your attention.
Thanks, Eric. Any questions, commentary? I must say that we had quite a lively discussion on the PC when this was first proposed. So, you know, we were hoping that that lively discussion would transfer into the audience as well.
Johnny Hain. So the general, comment that I have is, this is always good. The whole fight over routing header 0, I think, was misguided in terms of being too focused on badness and not focused enough on solutions. So this is a solution to a real problem. The one thing in terms of just the talk, you didn't discuss the issues with injecting the routing header and MTU size. Are you sending back?
Okay. Yeah, indeed.
Or possibly the extreme example you're using where you actually have the host inject the header, so then you don't have that issue. So if you could comment on that, I think it would help people who might not have thought about that. Okay.
So, and quickly, there is a big discussion there on the Spring mailing list on this at the IETF. So when it's initiated from the PC itself, from the source, of course, you don't get a real MTU issue because he knows it. Now, if you inject and the ingress of your AS, it's pretty much the same thing for MPLS network. You also inject additional header. So you need to design your internal AS having a bigger MTU, which is, I think, what people do anyway. Or you can send back ICMP packet too big and cross fingers, right? I mean, I would not dare to use pass-MTU discovery on this one.
Jeff Houston, after Philip's comment, I thought I'd actually bring up why I thought this presentation was heading close to heresy. There is a certain school of thought inside many internet service providers that once you pass me a packet, it's my business how I get rid of it, not yours. So the idea that somehow your policies on how I should handle the traffic trump mine, I would only do if you pay me a barrel load of money Because otherwise, my job is to get rid of the packet as cheaply as possible unless you pay me a huge amount of money, which you're not going to do. So that's this kind of issue of who's in control of the packet at any point. And does source routing kind of invalidate that model? We had this discussion way back in Shim 6, and the ISPs in the room went, how dare users say where their packet's going? I'm the ISP, it's my call. But that's not really the big issue.
If you allow me just on this one.
Yeah, sure.
Of course, if you do traffic engineering at beginning in your AS, you do it from some specific source, from people paying for it. So basically, you are adding value by doing traffic engineering, or you do traffic engineering for discarding the traffic for even a load. The goal of the service provider is to gain money on this one. So, but you have another question, right?
Yeah, the real heresy is actually addressing packets to the address of the router. You see, there's this whole issue of what's a control plane and what's a data plane, and how do I address internally in my network? Because one view of a packet-based network is the routers are never the destination. Mm-hmm. They're just the anonymous switching points. The things that are addressed are where packets start and where packets finish. And the reason why we burned source routing and loose source routing to a crisp in V4 and danced all over the ashes, dug a really big hole and put them all down there, was that when we thought about it pretty hard, this idea that routers had addresses that were reachable from the data plane seemed wrong. There's something sort of, I'm using up resources on the router, it becomes a point of DDoS, I now need to compute, I now have to take a packet that's addressed to me, figure out whether it's control or data, do a whole bunch of processing. What if I've got 1 billion packets a second? You know, where do I die? And this whole idea was I can stop this by never having packets addressed to me. I never have to process a packet in terms of reaching inside, I just need to get rid of them. And this idea of bringing back in the router as a target was the real point of heresy here. Okay. And all the desire to recreate the telephone network just seems anachronistic to me.
No, again, it's source routing within an AS. Okay, your question was pretty large, and there are multiple angles of attack there. It's source routing within an AS. It's not source routing from anywhere over the internet. That's basically traffic engineering. When any service provider does traffic engineering, it does the same thing. Regarding now revealing the IPv6 addresses of the router, I mean, traceroute does the same thing most of the time, right?
Not really. I'm like, if I number my network in 10 and someone does a traceroute, whoopee-doo, there's no information leak because the information makes no sense.
Or you can even use ULA in IPv6 if you want. But again, it's orthogonal. You can still, if you use addresses that are unreachable from the outside, let's say network 10 or ULAs, in the case of V6, right, let's be modern, those ULA addresses will not be reachable from outside of your AS anyway, because hopefully you don't announce this ULA prefix. You only use it, this ULA address of the segment routing within your AS once you reach your AS, right? So honestly, read the draft. That's very easy escape, right? Read the draft. All of those things has been very, very well defined. And I would welcome your comment, of course.
Thanks.
Thank you, Jeff.
All right, so thank you very much. Thanks very much for that, Eric. I think I should have put Eric's presentation first up in the agenda to wake everybody else up to ask questions of our other two speakers, but anyway, that's been very good. I forgot one thing. Maz, can you come and collect your speaker gift, please? Our other two speakers received gifts already, and I omitted. You found the path this time. That's very good. So, yep. There you go. Thank you very much. So thanks to all our three speakers. We're just about to enter the break. The session after here is the IPv6 plenary, and Sunny is going to say something about the other session that's happening as well.
Thanks, Philip, and good morning, everyone. I thought, I don't have to step up here today, but this is quite important. We have a slight change in the agenda this morning. The PPAC session that is scheduled in the next door room is not going to happen. But in the same time slot, Apnic EC is holding a formation of a cooperation, a SIG. This is modeled after RIPE NCC Cooperation Working Group, which we all know is very successful. We do understand that this formation of cooperation SIG is happening in parallel with IPv6 plenary in this room, but the SIG, that session is not going to take too long. It's just a short presentation, discussion thereafter, and it's a very short session. So we would encourage you to join that session and then come back into this room if you want to continue attending the IPv6 plenary. Why the Apnic EC is holding this session? We feel that internet regulation may have an impact on IP addresses, and this is where we need the cooperation of everyone. When I say everyone, it's the law enforcement agencies, the governments, the internet users, the operators, everyone. So we do encourage you all to attend this session, and in the Lincoln room at 11 o'clock, starts at 11 o'clock, and we hopefully finish by within 20 minutes or 25 minutes. Thank you very much. The morning tea is served just outside this room.
All right, thanks very much, everyone. See you at 11 o'clock. Sorry for the overrun. We did start a bit late, so if you can please be quick with your morning tea, we'll restart everything again at 11. Thanks.